Hawaii's lava flank collapse is a mega-tsunami waiting to happen. Scientists say 100-foot waves could hit the East Coast in 9 hours. But here's what everyone gets wrong about this threat. The Hawaiian slump, a 5,000 cubic mile chunk of Kilauea's south flank, is moving right now. Slowly, year after year, parts of it slide 10 centimeters seaward into the Pacific Ocean. It's not dramatic, it's not noticeable, it's relentless, and scientists have been studying it for decades because they know what could happen if that slow creep suddenly stops and everything above it lets go all at once. A complete failure could trigger the kind of mega-tsunami that doesn't just erase beaches, it rewrites coastlines. But the real story is far stranger than the disaster movie headlines suggest. And the probability question keeping geologists awake at night is one most people have never even asked. This is the untouched story of how a volcano in the middle of the Pacific could reshape human civilization on the opposite side of the world. Here's the thing about catastrophic geology. The worst-case scenario is always real, not theoretical. Real. The Kilauea volcano sits on the southeast coast of Hawaii's Big Island, and beneath its weight lies a weak foundation made of ancient rocks that cannot hold the volcano up forever. Older layers of basalt, softer materials, compressed sediments that have been slowly giving way to gravity for millennia. Gravity pulls that south flank toward the ocean with relentless pressure. Magma from deep inside the earth pushes it outward with tremendous force. The volcano grows, but it also fails in slow motion. Every few decades, something shifts. Every few decades, the ground moves in ways that people can measure with instruments and satellites. Every few decades, the warning lights blink a little brighter, but nobody beyond a tight circle of scientists really notices. The Hawaiian Volcano Observatory monitors these changes obsessively because they understand what's at stake. The Kilauea volcano is not like other mountains. It's not stable and static like the Rocky Mountains or the Appalachians. It's actively constructing itself, erupting lava that cools into new land, but that same process destabilizes what came before. The more the volcano builds upward, the more stress it places on the foundation beneath it. That's the paradox of growth. Construction breeds collapse. In 1975, on November 29th, the ground didn't just move, it shook. A magnitude 7.2 earthquake ripped through the Kalapana region in the early morning hours, and the entire south flank lurched seaward by multiple meters in a single violent shift that lasted less than a minute, but changed the landscape permanently. The earthquake generated a local tsunami with waves more than 47 feet high that crashed across the southeastern shore with tremendous force and power. Witnesses reported the ocean pulling back first, exposing the seafloor dramatically before the wall of water returned with stunning speed. Coconut palms ended up standing in the ocean when the ground subsided. The earth actually sank. The ground dropped so dramatically in places that some small offshore islands nearly disappeared beneath the waves entirely. In some locations, the vertical subsidence reached more than 11 feet. Houses were destroyed. Fishermen's boats were swept far inland. Families lost everything. The event killed 2 people and caused severe property damage across the southeastern part of the island. This was not a total collapse. This was not the Hawaiian slump releasing all its energy at once. This was a warning tremor. A magnitude 7.2 is enormous, but scientists knew then what they know now. The Hawaiian slump is much bigger and weaker and capable of releasing far more energy than what released in that November morning. Now zoom in on what that earthquake actually means in terms of the slump itself. The south flank of Kilauea moved. It shifted seaward. The weak layers that underlie the entire south side of the island couldn't hold against the stress. They slipped. They failed partially. Multiple meters of horizontal displacement occurred. Scientists measured horizontal movement of nearly 8 meters near Keauhou Landing. Vertical subsidence reached 3.5 meters. That's nearly 12 feet of the ground, simply vanishing downward as rock layers compressed and shifted under stress. That same year, the Pacific Tsunami Warning Center tracked the tsunami's propagation across the entire Pacific Basin. From Hawaii to California, it took hours. The warning system worked because people had already felt the earthquake. They knew a tsunami was coming. Emergency protocols activated. Sirens sounded. People moved to higher ground. But a flank collapse would be different. There might be no major earthquake preceding it. The slump might fail gradually or in slow motion or with only small foreshocks that wouldn't trigger automatic tsunami warnings. The first warning might be the sound of sirens triggered by waves already in motion, already traveling toward the coast. The slump itself is massive beyond intuition. 5,000 cubic miles. Let me put that into scale. Imagine a cube of rock and earth and volcanic material that stretches roughly 20,000 cubic kilometers into the subsurface. That's enough material to cover the entire state of Connecticut with a layer of rock a mile thick. That's a volume equal to roughly 3.5 Mount Everests stacked on top of each other. If you excavated it and spread it evenly across the United States, you could bury the entire country under a layer about 30 feet deep. It's bigger than Rhode Island. It's bigger than the state of Delaware. It's one of the largest UN-stable structures on any continent. And it's moving. The eastern flank of Kilauea slides seaward at rates up to 10 centimeters per year in some sections, about 4 inches annually. That might sound like nothing in human timescales. In geological time, it's a sprint. That's the equivalent of moving your entire house 4 inches per year, year after year, decade after decade. A century of that movement equals over 30 feet of seaward displacement. 1,000 years equals 300 feet. 10,000 years equals 3,000 feet, more than half a mile of horizontal movement. Eventually, the foundation beneath a half-mile of movement has to fail. The slump extends more than 4 kilometers, nearly 2.5 miles, beneath the ocean floor into the submarine geology of the Hawaiian Islands. Its front edge sits about 13 miles offshore, completely invisible unless you're operating specialized research submarines equipped with advanced sonar. Scientists using undersea mapping and bathymetry have identified the exact architecture of this geological time bomb. They've seen the layers. They've measured the stress fields using seismometers and GPS instruments. They've identified the fault planes that would rupture if failure occurred. They've even found something that might slow a collapse down, an undersea bench that formed as the slump scraped across the ocean floor over millions of years. This natural buttress could theoretically hold back the entire slump from catastrophic failure. But buttresses can fail too. They can be overwhelmed by accumulated stress. They can erode slowly over millennia. They can fracture from internal pressure. The question scientists keep asking is not whether the Helena slump will collapse eventually. In geological time, everything collapses. The question is, when? Will it be in 10,000 years? 100,000 years? Tomorrow? The uncertainty is the real threat hanging over all of us. Now scale this up to the collapse scenario itself. A complete detachment of the slump would displace somewhere between 2,400 and 2,900 cubic miles of rock. Different studies give slightly different numbers depending on how they define the slump's boundaries, but they all point to the same conclusion. That's roughly 10% of the Big Island's total volume hitting the ocean at once. Imagine 10% of all the rock that makes up an entire island suddenly relocating from land to sea in minutes. The tsunami generated would not be a normal wave. It would not be the kind of tsunami that rises and falls in a predictable pattern. It would be a pulse, an instantaneous rise in sea level spreading outward from ground zero at speeds exceeding 500 miles per hour. In the shallow waters around Hawaii, that pulse would compress and amplify. The water would have nowhere to go but upward, creating vertical walls of water that dwarf anything in recorded history. Scientists using supercomputer models have simulated what happens next when you input the parameters of a Hawaiian collapse into their numerical tsunami codes. The initial wave height in local areas could exceed 1,000 feet, not 100, 1,000 feet. Imagine the Empire State Building lying on its side in water. That's the scale of the immediate local impact. Waves tall enough to cover a football stadium placed vertically. Waves with enough energy to move boulders the size of houses across the sea floor, as if they were pebbles. Waves that would erase every structure on the Hawaiian Islands within minutes of impact. Every building, every road, every harbor, every memory. But the Mega-Tsunami would race outward across the Pacific, losing energy with distance from the impact zone, yet still maintaining catastrophic power. The physics of tsunami propagation means that energy spreads across a larger and larger wavefront as it travels, which causes the wave height to diminish. But the total energy content remains staggering. It's like pouring a cup of water into a larger and larger basin. The water spreads thinner, but it never disappears. This is where the math gets genuinely terrifying. The Atlantic coast of North America sits roughly 4,000 miles from the impact zone. Tsunamis cross the deep ocean at speeds comparable to jet aircraft, often exceeding 500 miles per hour in deep water, where the ocean floor is thousands of meters below the surface. Historical data from the 1960 Chilean earthquake, the largest earthquake ever recorded at magnitude 9.5, showed tsunami waves crossing from the epicenter to Hawaii in just under 15 hours. The waves traveled across the entire Pacific Ocean in less than a day and a half. Waves reached Japan in 22 hours. The propagation patterns are predictable because they follow the laws of physics and water dynamics. Wave speed depends on water depth. In the deep Pacific, that depth averages nearly 3 miles. Some scientists have modeled a Hawaiian collapse tsunami reaching the East Coast in as little as 9 hours. 9 hours from complete flank failure to 100-foot waves striking from Florida to Maine. 9 hours for evacuation orders to be issued, for families to flee inland, for emergency systems to actually function at meaningful scale. 9 hours, and then the ocean changes forever. If that blew your mind, every subscriber is automatically entered in our monthly giveaway for a branded hoodie. Details in the description. The east coast of the United States sits in a particular kind of danger zone from a Hawaiian collapse tsunami. The continental shelf drops gradually compared to the dramatic plunge of the Pacific floor. Waves slow down as water depth decreases. They grow taller as their speed diminishes and the energy compresses into a smaller volume. It's like water being forced through a funnel. The velocity drops, but the height increases. The amplitude builds. A wave that traveled 1,000 miles as a barely noticeable undulation in deep water could arrive at the shoreline as a wall of water dozens of feet high. The Atlantic seaboard has never experienced a mega-tsunami in recorded history. Most tsunami damage along the East Coast comes from distant earthquakes in Alaska or from local submarine landslides. No scientist has measured or documented what a 1,000-mile-wide wall of water actually does to the coastline from Virginia to Maine, what it does to Norfolk's naval fleet, what it does to Charleston's historic district, what it does to New York Harbor. The last catastrophic flank collapse event in the Hawaiian Islands happened 100,000 years ago, the Nu'anu slide, which detached from the north side of Oahu. That collapse generated waves large enough to deposit coral blocks the size of houses onto elevated cliff faces. Rocks that weigh thousands of tons ended up hundreds of feet above sea level, far inland from the shoreline where they originated. Scientists have found these blocks. They measured them. They dated the coral inside them using radiometric techniques. The evidence is unambiguous. 100,000 years ago, the ocean briefly rose high enough to carry multi-ton rocks to elevations where no wave should ever reach. That was one collapse event on one Hawaiian island, 100,000 years ago. The geological record is scattered with evidence of similar events. Beaches on the islands contain layers of shells, bones, and debris that clearly mark where giant waves carried ocean life far inland. This is not speculation. This is not modeling. This is archaeology. This is physical evidence written into the ground itself. And it all points to a consistent message. Hawaiian volcanoes have collapsed repeatedly throughout history, and when they do, the results reshape distant coastlines. The reason scientists take the Hawaiian slump seriously is not because a collapse is likely tomorrow, or next year, or even within our children's lifetimes. It's because a collapse is statistically inevitable over enough time. The Hawaiian slump has been sitting on Kilauea's south flank for hundreds of thousands of years, slowly accumulating stress. It will be there for hundreds of thousands of years more, continuing to accumulate stress. Sometime in that distant geological future, probably not within the next 10,000 years, but perhaps within the next 100,000 years, the equilibrium will shift. The conditions for failure will align. The buttress might fail. The weak foundation will give way completely. The accumulated stress will exceed the rock's strength. The 5,000 cubic miles of unstable rock will find the ocean. And when it does, the East Coast will have approximately 9 hours warning, 9 hours to evacuate, 9 hours to drive away from the shore, 9 hours to hope that the models are correct and the waves don't arrive any faster than predicted, 9 hours to protect yourself from the most powerful natural force on the planet. The current monitoring systems in Hawaii, the seismic networks that detect earthquakes constantly, the GPS stations that measure crustal movement with precision, the Pacific Tsunami Warning Center that tracks ocean disturbances and propagation, are designed to detect earthquakes within seconds and issue alerts immediately. A magnitude 7.0 or higher would trigger automatic tsunami alerts. Scientists can estimate wave travel times fairly accurately using numerical modeling, but there's a catch that keeps disaster planners up at night. When the tsunami reaches the coast, how much warning does an alert really provide? 15 minutes? 30 minutes? For coastal residents living within a mile of the ocean, that's not enough time to drive to safety. How do you evacuate an entire metropolitan area, millions of people in New York, Boston, Miami, in 9 hours? The highways would jam. The routes inland would become parking lots. Emergency systems are designed to handle regional disasters, not continental ones. A Mega-Tsunami from Hawaii would affect thousands of miles of coastline simultaneously. There's no good answer to the evacuation question, and that's what keeps this problem unsolved. What makes the Hawaiian slump story even more complicated is that it's not just sitting there passively threatening disaster. It's actively deforming. It's moving. It's reshaping itself moment by moment. Every time magma intrudes into the volcanic rift zone beneath the island, it pushes the flanks seaward with increased pressure. Every time lava erupts from Kilauea, new material adds weight to an already unstable structure. The structural stress accumulates. The 1975 earthquake moved parts of the slump by multiple meters at once, but it didn't trigger a full collapse. Instead, it released pressure locally, like a safety valve opening slightly to prevent a boiler explosion. The system reset. The movement stopped temporarily. Then it resumed, slowly, patiently, year after year. The volcano continues to pump magma from the mantle upward through the Hawaiian hotspot. The south flank continues to slide seaward. The buttress continues to erode in the deep ocean. Nothing in this system is static. Everything is in motion towards some future threshold that we cannot predict with precision. Scientists studying the Hawaiian fault system have found that major displacement events tend to happen together with the very largest earthquakes, magnitude 8.0 or higher. That's a critical constraint they've identified through decades of research. A full catastrophic collapse might require not just pressure from magma and gravity, but also a powerful trigger. a massive earthquake to suddenly release all the accumulated stress at once. But the deep ocean around Kilauea can rupture. The seafloor can shake violently. Offshore fault systems exist that could easily produce large earthquakes. The conditions for that powerful trigger exist and always have existed. The probability might be low in any given century, but across millennia, it becomes inevitable. And when it happens, the warning sirens will sound loudly, and people on the East Coast will have exactly 9 hours. The honest assessment from the United States Geological Survey and from volcano researchers at the University of Hawaii is that catastrophic flank collapse in the next few centuries is considered unlikely. The phrase used in scientific literature is deliberately cautious and measured. Unlikely, not impossible, not implausible, unlikely, which means probable in the longer geological term. The statistical models suggest maybe one such event per 100,000 years across all of Hawaii's volcanoes. But those averages are meaningless when you're standing on the island when it happens. The probability becomes 100% at the moment of failure. The buttress system that's slowing down the slump, that undersea bench that formed as the slump dragged across older rocks, might actually be stronger than some models suggest, or it might be weaker. Nobody knows for certain. Undersea surveys have identified it, but measuring its actual rock strength from a research vessel is nearly impossible. Scientists have to estimate, they have to model, they have to make educated guesses about whether rock formed millions of years ago will hold for another 10,000 years or fail next Tuesday morning. That uncertainty is the real problem, not the worst-case scenario itself. The uncertainty about when it will occur. And if stories like this remind you that the unexpected can arrive without warning, grab your free disaster preparedness toolkit. The link is in the description. Right now, the Helena slump is moving. 10 centimeters per year. 6 inches per year in the language of our daily experience. You cannot feel it. You cannot see it. The volcano is not erupting in dramatic lava fountains. The ground is not visibly shaking in ways that alarm people. Everything appears stable and permanent and normal. Daily life proceeds normally on Hawaii's Big Island. Tourists visit. Families live. Children are born. And below the surface, below the ocean, below the buttress, in the weak rock and old foundations beneath the island, an enormous weight continues to shift seaward. Scientists monitor it constantly. Governments plan for it. Emergency managers strategize about it. Insurance companies price risk around it. And most of the East Coast has never heard of it. Most people planning vacations to Hawaii don't know they're standing on an island undergoing permanent, relentless deformation. Most Americans living along the Atlantic shore have no idea that 9 hours of warning is all they would get if the Helena slump suddenly decided to fail. The vast majority of the planet has no concept whatsoever of this threat that could reshape an entire coast in less than half a day. The most unsettling part about catastrophic geology is not the scenario itself. It's not even the scale of potential destruction. It's the waiting. It's knowing that the ground you're standing on, that the island you're visiting, that the coast you're defending is all part of a slow-motion disaster that will happen eventually. Probably not today. Probably not in our lifetime. Probably not for many thousands of years. But inevitable. Always inevitable. Always waiting. The Helena slump will move. The stress will accumulate. One day, the balance will shift. One day, the ocean will change. The Hawaiian Islands are not done moving. The volcano is not done growing. The foundation is not done failing. Until then, we watch. We wait. We monitor. We prepare. We hope that when the threshold is crossed, we've done enough. We hope that our warning systems work. We hope that our models are accurate. We hope that when the first tremor hits, there's enough time. And we know, in our bones, that 9 hours is not nearly enough time. But we do it anyway. We prepare. We wait. We watch. And the island, indifferent to our worry, continues to move seaward, relentless and patient, waiting for the moment when gravity finally wins.